When it comes to combinations, very much like permutations, they're arrangements of objects. With combinations, however, order does not matter, where permutations order did matter. So how we calculate combinations is very similar to how we calculate permutations, with one slight difference. For instance, we want to find out the number of combinations of n things taken r at a time. What we do is set up a fraction where the numerator is our n things factorial. Then we're going to divide off by n minus r factorial. And that's what permutations look like. How combinations look a little bit different is we also tack on this r factorial at the end, and that divides off all the order, where order doesn't matter. Now, what that means for us is if we want 10C7, so that's 10 choose 7, or we have 10 things and we want to take 7 of them at a time, the number of ways that we can take 7 things out of a group of 10, in which order doesn't matter, is we start off with 10 factorial in the numerator, and then do 10 minus 7 in the bottom, times 7 factorial. So that'll leave us 10 factorial over 3 factorial, 7 factorial. Now how we calculate that, remember 10 factorial is 10 times 9 times 8 times 7, all the way down to 3 times 2 times 1. Then we'll have 3 times 2 times 1, and 7, 6, 5, 4, and I don't really need to write all this. Instead, what I'm going to do with that 7 is just call it 7 factorial, because that 7 factorial is going to cancel with all from 7 on down in the numerator. Then we also got a little more canceling to do. 3 goes into 3, or into 9 3 times, and 2 goes into 8 4 times. So then this is all we really need to multiply out, and we get 10 times 3 times 4 is 120. Different ways that we could use 7 objects out of a group of 10. So one good example where order doesn't matter is when you're talking about drawing cards. Because usually what happens, you get dealt cards and then you mix them up anyway, so the order that you dealt the cards doesn't matter. So how many ways can we get 4 cards out of a standard deck of playing cards? Well, a deck of playing cards has 52 cards in it, and we want to take 4 out. So that'd be 52 factorial, or 52 minus 4 factorial, and 4 factorial. So that'd be 48 and 4. What we might notice is that those denominators, they always add up to make the numerator. But anyway, we'll multiply it out. 52, 51, 50, 49, and I'm going to stop at 48 factorial. I know it goes the rest of the way down, but I have that 48 factorial also in the denominator. 4, 3, 2, 1 takes care of the 4 factorial. So right off the bat, those two cancel. Now we need to look for pieces, like 4 going into 52 13 times. 3 goes into 51 17 times, and 2 goes into 50 25 times. So now it's a lot less stuff to calculate, but you plug it all into your calculator and you get 270,725 different 4-card hands that could be made. One thing I forgot to mention, but this 52 choose 4, that's in your calculator. It's right next to NPR, it's NCR, and you can find that under the math menu. I'll let you do that on your own. Let's move on to how many ways could you get 4 cards to all be from one color. Well, with a standard deck of cards, there's 2 different colors that are there, red and black, and in each color there's 26 cards. So there'd be like, if we say red, there's 13 diamonds and 13 hearts. That makes it 26 cards. And we want to take 4 of them. Well, and be 26 factorial over 26 minus 4, which is 22 factorial, and 4 factorial. Multiplying it all out, 26, 25, 24, 23, and 22 factorial over 22 factorial, and 4, 3, 2, and 1. So those guys cancel. And 4 times 3 times 2 is 24, so that'll cancel with that. And we just multiply those out. 26 times 25 and 23 gives us 14,950. But now remember, that was just a number of ways to do the red cards. We could have also picked the black card, so we really need to take this number and double it, and we'll get 29,900 different ways. Now this is a situation where we really had a couple of different things happening at one time, where first we had to pick the color actually, and then also pick the 4 cards out of that color. So this is what we call multiple events, and there's a couple different ways this can happen. First of all, the one we're talking about now is if one thing happens and then another thing happens. For instance, in this last problem, we had to pick a color and pick 4 cards. Okay? Now what we should do then is find the number of ways to pick the color and multiply it by the number of ways to pick the card. So how we would set that up, there are 2 colors in a deck of cards, and we need to pick one of those. I'm going to take that result and multiply it by the 26 cards that are in any color, and we're going to take the 4 cards out of it. Now, I'm not going to multiply this all out. You could do this on your own, but what you'll get is 2 times 14,950, which were those same 2 numbers that we multiplied before, and we get 29,900 different ways. Let's take a look at another example. With Shakespeare, who wrote 28 plays, 18 comedies, 10 histories, 10 tragedies. How many ways can we get exactly 2 comedies and 1 tragedy? So this is again a time where we're looking for an and situation. So the number of ways we can choose exactly two comedies. Well, out of the 18 comedies that there are, we want to take 2 of them. And means multiply. Number of ways we can get a tragedy. Well, there are 10 tragedies, and we want to get 1 of them. Once again, we just multiply these out. That would be 18 factorial, 16 factorial, and 2 factorial. And over here we'll have 10 over 9 and 1. So, once again, I stop at 16 factorial because I have 16 factorial in the denominator. And here I'll stop at 9 factorial because I got 9 factorial in the denominator. And look for things to cancel. Of course, the factorials cancel right away. And 2 goes into 18 9 times. So, multiply those out. 9 times 17 times 10. We get 1,530 different ways. But what if we don't want 2 events to happen? What if we want 1 of 2 events to happen? For instance, going back to the picking 4 cards of the same color. Well, what we could have done is looked at it as how many ways could we pick 4 black cards or pick 4 red cards? Well, we could go about it by there are 26 black and we want to take 4 of them, or 26 black and we want to take, or 26 red and we want to take 4 of them. Now we've already calculated this out a couple times, but that's 14,950 different ways to pick black cards, and there are 14,950 different ways to pick the 4 red cards. So we can add those two amounts together and get that same number of ways, 29,900. So basically, if it's an and situation, we're going to multiply. If it's an or situation, we're going to add. For example, with the same Shakespeare plays, how many sets of at most 3 plays could you choose? Now, that doesn't sound like and or right off the bat, but if you think about it, if we want at most 3 plays, we could pick 0, or we could pick 1, or we could pick 2, or we could pick 3. So set it up as out of the 28 plays, we want to choose 0 of them, or out of the 28 plays, we want to choose 1. Or out of the 28 plays, we want to take 2. Or out of the 28 plays, we want to take 3. Once again, I'm not going to go through all the multiplication here, but this is going to be 28 factorial over 28 factorial 0 plus 28 factorial over, now that's 0 factorial, which would be 1, and over here we'll get 27 factorial 1 factorial, then 26 factorial and 2 factorial, and finally 25 factorial and 3 factorial. I'll let you calculate that all out, and you should get 3,600 683 different ways. For the second half of this video, I want to talk about the binomial theorem, which first starts with a discussion of Pascal's triangle. Pascal's triangle is a triangle of numbers. Each row begins with 1 and ends with 1. How we get every other number in the row is we're going to add those two above it together. So to get to the next row, we'll start and end with 1. Add together 1 and 2 to make 3, and 2 and 1 to make 3. Start with 1, add the 2 together, make 4. Add 3 and 3 to make 6. 3 and 1 is 4, and end with 1. 1, 5, 10, 10, 5, 1. The thing about Pascal's triangle is that it's really beautiful because it's simple. It looks pretty. There's a ton of patterns in it and a ton of applications. As far as patterns go, we notice that like I said, we always start and end with 1. And if we look at the second row, that goes 1, 2, 3, 4, 5, and 1, 2, 3, 4, 5. And there's all this symmetry that if you drew a line right down the middle, the left half of the triangle looks just like the right half of the triangle. But there's more important things to it too. And as far as binomial expansion goes, each of these rows have another corresponding thing that's really important. For instance, this first row is 0, choose 0. For each element in the second row, that starts with 1, and we're going to choose 0, or 1, choose 1. For the third row, that's not 1 anymore, but now 2, choose 1, 0, 2, choose 1, and 2, choose 2. For the third row, 3, choose starting with 0, 1, 2, and ending with 3. And that continues all the way through. This helps us with the binomial theorem. And what the binomial theorem is a way to expand a binomial taken to a power. Now normally what would happen is if we had like x plus 5 squared, that's not a problem. We could FOIL that out. X squared plus 10x plus 25. That's not a problem. Even if we had x plus 5 to the third, that's really not that big of a deal either, because we would just take this and multiply it by another x plus 5, and we could see how to do that. But what about if we continue on down and we want to do x plus 5 now to the 8th power? Now it's getting pretty big. There's a lot of room for error, and I wish there was a way that we could simplify this real quickly. And that's where Pascal's triangle helps us out, or looking at it in terms of those combinations. See, if we have a plus b, a two-term binomial taken to the nth power, the first term is going to be n choose 0. A is taken to the nth power, b is taken to the 0th power. For the next term, n choose 1. A gets reduced by a power, and b is now at the first power. For the next term, n choose 2. A gets reduced again, and b is now up to 2. And this is going to keep going all the way down to n choose n minus 1, and then be a to the first, b to the n minus 1, and n choose n, a to the 0, b to the n. Right. That looks a little complicated right now, but remember, each of these little pieces right here correspond to a row of Pascal's triangle. Then when you look at A and B, their powers for A starts at the power of the binomial right here, and it goes down by 1 all the way down to 0. For B, it starts at 0, and its power increases by 1 all the way up to n. That'll help us when we want to do something like expand x plus 3 to the 4th. First, I'm going to write it out the long way. We're going to start with 4, choose 0, x to the 4th, 3 to the 0. The next term is going to be 4, choose 1. Then x reduces its power by 1, and 3 is now to the first. As we keep going, 4, choose 2, x squared, 3 squared, 4, choose 3, x to the first, 3 to the third, and finish up with 4, choose 4, x to the 0, 3 to the 4th. And this gives us a way to start multiplying all of those coefficients. Remember, this corresponds to one of the rows in Pascal's triangle. And the thing about Pascal's triangle is that it always started off with 1. We'll have x to the 4th, and 3 to the first power is also 1. The next one, the next term would be 1, 2, 3, 4, 5, something like that. And since we're talking about 4 choose 1, that means the next term is going to be 4. X to the 3rd power times 3. Now that we're at 4 choose 2, maybe we actually have to calculate that out as 4 factorial over 4 minus 2 factorial times 2 factorial. X squared times 9. Then the symmetry starts happening. 4 choose 3 is the same as 4 choose 1, so we're back to being 4x times 27, and we end up with 1. X to the 0 is 1, and 3 to the 4th is 81. So we only have a little bit of calculating to do to simplify this out. But 4 times 3 is going to be 12. I'll let you calculate 4 factorial or 2 factorial times 2 factorial, but you should get 6. And then we'll have 4 times 27 again, and 81. So we just finish it up real quickly. And there, we've expanded x plus 3 to the 4th power without having to take x plus 3 times x plus 3 times x plus 3 times x plus 3. Let's do it one more time with something a little bit more complicated. 2x minus 4 to the 4th power. Well, let's do a slightly different power just to change it up a little bit. But let's do it to the 3rd. If I'm going to have you use a binomial theorem, I'm not going to have you expand something to the 10th power, something that's ridiculously huge. So keeping it to maybe the 5th power or less would be reasonable. Anyway, how are we going to set it up? Well, we start with the power, so it would be 3 choose 0. Then we have to take the first term, which in this case is 2x, is going to the 3rd power. The next term is negative y, goes to the 0. As we continue, 3 choose 1. Now, 2x is to the 2nd power, and negative y is to the 1st. 3 choose 2. Same bases, 2x and negative y, but now 2x to the 1st, negative y to the 2nd, and then finish it up with 3 choose 3. 2x to the 0, and now negative y to the 3rd. So there's a lot of things to pay attention to beyond just these coefficients. Pascal's triangle helps us with those coefficients. Remember, the first one is 1. The next one would be, since we're talking about 3 choose 1, that would be 3. And we're past the midpoint, so this would be 3, and this would be 1. And that's the row in Pascal's triangle, 1, 3, 3, 1. But now we have to multiply out the other things. So 2x to the 3rd power is really 8x cubed. And anything to the 0 is just 1. In the next term, 2x squared is 4x squared times negative y. 2x to the 1st is just 2x. But negative y squared is now positive y squared. And then we finish up. Anything to the 0 is just 1. But negative y cubed is like negative y cubed. So all of those even powers of a negative number turn positive, and all the odd powers turn negative. Anyway, we just finish it up by multiplying. 8x cubed, not plus, because we'll go 3 times 4 times negative 1, which is negative 12, x squared y. And then 3 times 2 is 6, xy squared. And 1 times negative 1 is negative y cubed. And there's how we expand 2x minus y to the 3rd. Last thing, sometimes we might want to find one specific term in the expansion of x minus 2 to the 10. So if we want to find that x minus 5th term, remember that with the binomial theorem, we're always going to start off with 10, choose something. We want x to the 5th term, but think about it. It starts with x to the 10th, then x to the 9th, x to the 8th, 7th, 6th, and then 5. So if we want that x to the 5th power, that's really the 6th term. Anyway, as we continue, now x and -2 have to be taken to different powers. Okay, this is the very last thing, and I already screwed up on this little piece of information that we started off with. So, I'm not going to redo this whole video. Instead, let me start this one problem over. Find the coefficient of the x to the 5th term in the expansion of x minus 2 to the 10th. And when we're talking about the binomial theorem, we do want to start with the power, choose something. We want x to be to the 5th, which means this thing has to be to the 5th as well, because those two powers have to add up to the total of 10 power. And one last thing about the binomial theorem. If we go all the way back to the definition, you might notice that this number is the same as this number. So here when we had 1, that was the same as this number. All the way down to the end. And -1, that's the same as the second term. So in our example, what do we need this to be? Well, the same as that one. So this is going to be 10, choose 5. So we go ahead and calculate that. 10 factorial over 10 minus 5 factorial times 5 factorial. X to the 5th and -2 to the 5th. That'll be 10, 9, 8, 7, 6, 5 factorial over 5 factorial and 5, 4, 3, 2, 1. Times x to the 5th times -32. So you get to canceling. 5 and 2 make 10. 4 goes into 8 twice, and 3 goes into 9 3 times. So I'm going to multiply 3 times 2 times 7 times 6, and also times that -32, which means we'll end up with -8,064 x to the 5th. The question is, what's the coefficient? Here's the coefficient, just the number out in front.